Electric current speed. Think different. 4. In the previous video, we have discussed about why friction can cause static charge and why power generators can produce current. The frequently variation of the magnetic field causes most electrons in the conductor change their spins to one same direction. Then the charge repulsion and magnetic repulsion among them push them apart. Either squeeze to the tip or to the surface of the conductors, or move away along the wire. Thus, electric currents start. From the microscopic point of view, in metal conductors the electric current is like a team of ballet dancers. Every electron, spins in the same direction, and moves toward one direction, the electric current direction. Their heads and feet are the direction of the electric current magnetic field. The directions of magnetic field and current are perpendicular to each other. In semiconductors the electric current situation is different. Atoms are arranged in crystal lattice. Electrons' delocalization is not as freely as metal conductors. In N-type semiconductors some atoms have extra electrons than others. In P-type semiconductors some atoms have fewer electrons than others. The boys represent the atoms in a P-type semiconductor. They are arranged in a crystal lattice. The first boy has no hat, electron deficient, and others after him all have hats. When the electricity is applied, the second boy gives his hat to the first one and becomes bareheaded, electron deficient. The third boy then in turn gives his hat to the second boy and becomes bareheaded, electron deficient. One by one continue on, till the last boy becomes bareheaded, electron deficient. Then the positive charge is transferred from the first atom to the last atom. In N-type semiconductors, some atoms contain more electrons than others. Like, the first boy has an extra hat. When the current starts, the first boy puts the extra hat on his head and hands the original hat to the second boy. The second boy puts the new hat on his head and hands the old hat to the third boy. And so on, when everyone does the same action at the same time. Extra hats are immediately passed from the first boy to the last boy. This can be thought of as electron tunneling. The description shows that the electron transfer speeds of P-type semiconductors and N-type semiconductors are very different. The above are the electron transfer situations in solid metals and solid semiconductors. How is the situation of electron transfer in liquid? Nobel Prize winner Marcus Rudolph, the professor of physical chemistry at the University of California, USA, derived a formula of electron transfer speed of chemical reactions in the 1950s. K, ET, is the rate constant of the electron transfer. H, AB, is the electronic coupling between the initial and final states. Lambda is the reorganization energy of the reactant. B, is Boltzmann constant. H, pi, is the reduced Planck constant. -0 is the Gibbs free energy change for the electron transfer reaction. T is the absolute temperature. In formula 2, if take H, AB, and lambda approximately as constants, the logarithm of the reaction rate constant log K, ET, shows a quadratic curve in relation with lambda plus delta G0, reorganization energy and the Gibbs energy change. The figure of formula 2 is an inverted quadratic curve. On the left side of the curve, the reorganization energy lambda larger than the Gibbs energy, minus delta G0, the reaction rate gets faster as the Gibbs energy increases. This is the rising part of the parabola. The right side of the curve, the reorganization energy lambda less than the Gibbs energy, minus delta G0, the reaction rate slows down as the Gibbs energy increases. It is the descending part of the parabola. When the reorganization energy lambda equals the Gibbs energy, minus delta G0, the reaction rate reaches the apex. At this time the reaction is spontaneous. According to the three reaction KET situations, draw three reaction precession diagrams. It shows the reactant system and product system potential energy curves crossing situations in the following three conditions. 1. Minus lambda plus delta G0 less than 0, 2. Minus lambda plus delta G0 equals 0, 3. Minus lambda plus delta G0 larger than 0. The three situations correspond to the rising, maximum and declining zones of the reaction rates. Because the formula predicts an abnormal situation. Reaction rate declines when Gibbs free energy increases. Scientists are eager to experimentally prove the reversal zone. However, all experiments only prove the rising zone of the parabola, that is, ideally, the reaction speed accelerates as minus delta G0 increases, but when the reaction speed increases to a certain extent, it becomes a constant, forming a parallel line, no matter how minus delta G0 increases. Till more than 30 years later, Dr. Miller, Calcaterra and Claus obtained the descending part of the formula curve by experiment. They used intramolecular electron transfer experiments. In their experiments the electron donor and electron acceptor parts were rigidly spaced to maintain a constant distance. At the same time, people also found the failure reason for the previous experiments. The charge transfer in solutions relies on the ions moving, and the ions are surrounded by solvent molecules. Ions' moving speed cannot exceed the solvent molecule's diffusion movement. Therefore, the electron transfer speeds in the previous experiment only rose to a certain level and then stopped increasing. Based on these findings, Professor James Bolton of the University of Ontario in Canada wanted to use the chlorophyll photosynthetic reaction to prove this formula. Professor Bolton planned to test intramolecular electron transfer reaction through a series of synthesized molecules. One side of the molecule is porphyrin, a light-sensitive component that simulates chlorophyll. When exposed to light, its electrons absorb energy, jump to a higher energy level and ready to transfer the electron as an electron donor. The other side of the molecule is benzoquinone. It is an electron acceptor group of the molecule. The two groups are linked by a series of amino acids. The original plan was to use 7 amino acids as the link. Test their intramolecular electron transfer speeds after exposure to light. Since the electron transfers within the molecule, it was expecting Marcus' kinetic formula could be proved too. But the synthesis of new compounds is quite a big job. To find the right reaction condition and product certification take time. The idea of synthesizing 7 compounds was later changed to synthesizing 1 compound and testing its electron transfer speed in different solvents. 2 doctoral students participated in this project. Each one synthesized a new compound PAQ and PPAQ. P and Q represent the electron donor porphyrin and the electron acceptor benzoquinone. A represents alanine, the amino acid linked in the middle. And PA represents phenylalanine. The 2 compounds underwent intramolecular electron transfer reactions in a series of solvents after illumination, and the reaction speeds were measured. However, the experimental results were not as expected. Because the synthesized molecules do not have a rigid structure, the distance between the electron donor and acceptor changes and is affected by the solvent molecules. The reaction speeds do not follow the Marcus formula equation. However, the experimental data shows two characteristics. 1. The electron transfer reaction speed is fast in solvents that contain heavy atoms, chlorine, bromine, and iodine. 2. The electron transfer reaction speed is also fast in solvents containing benzene rings. In order to confirm the influence of aromatic solvents and heavy atom solvents on the electron transfer speed, repeated the experiment in solutions of mixed solvents with different proportions. Experimental data show that the heavy atom solvents can speed up the electron transfer more than the aromatic solvents. Summary. Electric current is carried by electrons in solid metals and semiconductors. Electric currents are generated by magnetic field frequently and regularly change. Those changes can be external, power generator or transformer, or by other electrons. Magnetic field's variation induces electrons in solids to flip their spins. The same spin direction electrons are pushed apart by the charge repulsion and magnetic repulsion, thus producing an electric current. Electric current in solutions is different. Solutions consist of solutes, salt, and solvents, water. Electric current in solution is carried by ions. Hydrogen ions, protons, have spins and are also magnetons. Nuclear magnetic resonance tests confirmed it. However, it is not clear whether big ions, of several atoms, can exhibit overall spin and magnet. The current speed of ions in the solution is limited by the diffusion movement of solvent molecules. Electron transfer within the solute molecular may not be affected by the solvent diffusion movement. But the heavy atom solvents and aromatic solvents can accelerate the intramolecular electron transfer. In the batteries, electrons transfer through several steps. 1. From the cathode, solid, enter the medium, solution. 2. Move in the medium, solution. And 3. Enter the anode, solid, from the medium, solution. Keep the electron moving speed relatively consistent in all steps and avoid accumulation and blocking can improve the battery efficiency. Thanks for watching. Goodbye.